So hi everyone, welcome to this next session. We have Suresh Krishnan here from Kaloom. And today we'll be talking a little bit about 5G, the edge, and how P4 is helping to enable some new and exciting technology.
Excellent. My name is Suresh Krishnan. I'm the CTO of Kaloom, and we've been working with P4 for a very long time, like using programmable chips and like building an ecosystem of hardware, software, and like function to like do a lot of things in 5G. And one of the important changes that is happening over the past few years is like the move to the edge, kind of driven by 5G at one end and actually moving of applications to the edge as well on the other end. And that's kind of what I want to talk about today, like how we started off with like pretty much everything that's open source, and then moved on to do 5G at the edge using these things as the foundation. So I want to talk about like three facets of openness, right? Like, so one of them is like really like open hardware, open software, and open interfaces. Like, so starting off really, we want to do like ideally like a mix of all these things to make sure like things are really open and like, there's no vendor lock-in and so on. So I just want to run through these things and try to talk about like, what each of these entail to make sure that we can build like a completely open system. So let's start off with like open software, right? Like, so we have chosen to use standard off-the-shelf Linux as the operating system that we use for networking. So this is like kind of a little bit different from like a lot of the incumbent vendors in the networking industry who kind of spent a lot of time and effort to kind of like fine-tune a specific operating system for their networking hardware to kind of like squeeze out like every ounce of performance from the systems, right? But the problem becomes, it becomes like a little bit difficult to manage if you're a customer. So you need to have like different kind of mechanisms for like training people for the hardware, for the networking, for the compute, and for the storage. Like similarly, you cannot use the same kind of orchestration models for everything. So like we thought like uniformity is like a key thing to go for. So we try to use like regular Linux, off-the-shelf Linux. So we use, for example, we use something that's called CoreOS, RHEL CoreOS as the operating system that runs on the switches. So the switch pretty much boots up like any other server hardware, except that it has like a really high performance networking subsystem underneath, right? Like, but otherwise it like acts like a server, like, gets operating system installed on it like a server. It gets patched like a server. So that brings me to the next thing. So like, whenever there's some kind of security issues, like it's always about the weakest link. So we want to make sure that the system we run on the networking side doesn't become the weakest link in the whole system. So here we can use the same kind of patching mechanism, same kind of security mechanisms, for example, like SE Linux, like, the C groups and network namespaces and so on, to protect the networking the same way that we would do for compute. So like the networking doesn't become the weakest link in the system. And similarly, like, we can have the same kind of upgrade mechanisms and rollback mechanisms to like run in the system. And also, we are also trying to minimize the footprint of the system. And we do everything in a cloud native containerized fashion. And we wanted like a lightweight operating system to do it. And that's kind of why we went with CoreOS as the operating system, because we want something that's like minimal, lightweight, and able to run containers as like a native primitive. So next thing is like comes to the programmable data plane. So like, as I said before, like, we are like strong believers in P4 and kind of we've drunk the Kool-Aid, like totally sold on it, right? And we thought like, everything we're going to do in the fast path is pretty much going to be P4. So like what it gives us is really, it gives us like, the ability to add new features and services like at runtime without actually impacting the traffic. And it also allows like us to develop like, code very, very quickly and like do innovative stuff like, which we cannot do with like either like purpose-built ASICs or with something that's like a very, very generic kind of solution to do it in a performant way. And this also allows like vendor lock-in. Like it actually completely stops vendor lock-in. and eliminates the need to wait for silicon upgrades. So like, if you are waiting for an ASIC to be spun to support something, it's going to take a while before you can get to there. So like, we strongly believe that we can do some kind of DevOps model for networking. When there's like a new protocol or a protocol change that comes out, we want to be able to deploy it very, very quickly towards the customer networks. So not that like everybody is going to upgrade every like month or 2 months or like, every build, but the idea is like we'll be able to deliver features on the hardware with high performance even after you actually ship the hardware to the customer, or the customer bought the hardware from somebody else. And the other angle to this is like, we really want our customers who are like going to be the mobile network operators, the data center operators, like large enterprises and so on, to be able to do their own programming for some of the features they need. So this could be either because this is like a very specific feature they need, or this is something very proprietary and they don't want a vendor to know. Like, we want them to be able to do their own P4 code and host it on the fabric and using P4 runtime and so on. So that's something like, we are getting there. So we don't have like that much free room in the pipeline today to be able to do that. But we do have plans to open this up to like either like our customers or to other third-party vendors who can host network functions in the system. So this is all made possible by having a programmable data plane. And of course, like, we want to do something that's industry standard, because like, talking about programmability and talking about something proprietary doesn't really make sense. So we wanted to go with something that's like industry standard, and it also kind of gives us the hardware independence to run on multiple kinds of hardware. And I'll tell you why in a second. So so talking about open hardware, we really want to run on open source hardware. So like the pretty much every hardware we run on is like a open compute reference design. So like it's most of it is like really Barefoot Tofino, the Intel Barefoot Tofino based systems, and based on like standard OCP reference models. And this again, like, it avoids vendor lock-in and like allows like customers to pick from multiple vendors or the same kind of reference design. So people might have like some minor changes. For example, somebody might put in like a Xeon D class CPU in there, like on the control host. They could put more memory, swap in a hard disk for an SSD and so on, or like have better BMCs. But like really, like the idea is like these things are like really interchangeable, and people kind of compete on like the add-on features, not just the basic feature set. So this allows us to have like a large set of like boxes we can run on, and as long as they're programmable. And we also try to use standardized tools for hardware management. So like, all the stuff we do to boot, like, the system, like, we use ONI for it. So we can actually put like the initial software on the boxes in a very standardized way. So this allows us to do like, fleet management and actually run like a large number of customers, like without having too many issues, because it's pretty much standardized across the board, instead of trying to do like specific kind of boot sequences for specific kind of hardware. Similarly for BMC, like, for handling, the fans and LEDs and so on, and pretty much controlling the hardware of the system, we want to use like IPMI stuff and like, stuff like Redfish. So we are trying to do like standardize on the software stack for managing the hardware as well. And the like really the final piece is really like open interfaces. Like, we strongly believe in open interfaces. So it doesn't matter if like, we pick like, everything that's open source. We strongly believe that like, a lot of people are going to pick a mix of vendors to do things. And we want to be able to interoperate with like other pieces in the system, whether it's closed source, open source, like, and so on. And there's like a lot of investment that's also been put into a lot of these things, and we want to keep like standard interfaces going in all directions. So, so for example, right, like, everything we configure in the system is done using a Confinyang, and we use like standard models like from IETF to do the configuration of the system. So like, this is not like some new kind of like, CLI somebody needs to learn, or like it's not something proprietary that's going to go away. So like we try to stick as much to standards as possible, and using standard protocols and standard data-driven models. And similarly, like towards orchestration, right? People need to orchestrate workloads in the system, and we provide like interfaces towards like the two most common ones, like, Kubernetes, like, and we specifically use OpenShift, which is like a Red Hat distribution of Kubernetes. And we use a CNI interface to set up the networking interface for like any kind of containers that need to run on top of the networking. And similarly for OpenStack, we use ML to do the networking for OpenStack to get all the workloads plumbed together. And specifically in 5G, again, like the 3GPP has done like a wonderful initiative called CUPS, Control User Plane Separation, where they split the control plane from the user plane. So this has been happening for quite a while in data networks, right? Like IP networks, where there's like a routing processor and like the line cards. So the similar kind of thing has come to pass in 3GPP networks. It started off with like 4G. So like, the P gateway U and P gateway C separation happened. And the same separation is like something that's being done for 5G too. So there's like an entity called the SMF that does the control. It does like, the session management and so on. And an entity called the UPF that does the actual packet processing for the data. So we use a standard interface like towards our data plane, which is like the UPF, to talk to any kind of session management function that's there using the N4 interface. And that's really like a protocol that's called PFCP, and it's like standardized by 3GPP. So we use that. Similarly, towards the radio network, we use like the N3 interface. It's pretty much based on, again, another protocol called GTP. And again, standardized, so we can run towards any kind of RAN vendor. So it could have like an Ericsson RAN or Nokia RAN or a Samsung RAN, and we'll be able to run everything towards them. Or like, even like we are also working with stuff like, Open RAN and Open Air interface, so we can run pretty much any kind of disruptive RAN solution as well in a very standardized manner. And N6 is like something that's like very IP related stuff. So it's kind of like a interface towards an enterprises network, like a VPN, or towards like the internet. And this is all, again, standard like IETF based protocols. And we strongly believe in implementing those things and interacting openly towards whatever vendors are present on the other side. And the final piece of this, like when we started off with like, the programmable data plane, one of the things we realized is that like all hardware is not made equal, right? Like, a different kind of hardware has like different sweet spots. So for something that's like, extremely high throughput and low latency that's required, an ASIC like Intel Tofino is like a really, really good fit. So if you want to have like a few more functions on top of it, and you want to kind of have like a little bit more state, right? Like, so if you want to scale the number of sessions, or like, have for like a load balancer or a firewall or a UPF where you want to have like millions of sessions, an ASIC is like simply not going to cut it. So you need to really scope up and do something like an FPGA, which provides like quite a bit of memory on board and also additional logic, right? Like so you can do like higher layer functions on top of it. So we can do bring in like an ASIC into the picture and an FPGA into the picture as well. And of course, like, the x86 Xeon CPUs, for example, are like, excellent at doing like very, very high layer functions. So if you're trying to do something like DPI or like, higher layer functions in L7, application load balancers, for example, we need to bring in like a x86 kind of system. So our goal is to make sure that we can write code once and run the code in multiple kind of hardware. So right now we have stuff working where like the same kind of P4 pipeline is running on a Tofino, x86, as well as like an Intel FPGA, right? So like, we are able to do write the code once, test it once, and then like do like hardware specific backends, so we can build out the hardware based on what characteristics are required. And we have some kind of like hardware, open source hardware planned for this too, like where we can actually have different kind of pluggable modules that can let you pick and choose between different kind of hardware, but that's a little bit further out. So moving on to like 5G. So just like kind of like a very quick recap of 5G. So I assume like most people like, who are going to be in this presentation have like a basic understanding, but there's some few key things about 5G that I want to emphasize before like we go forward. So like one thing is like, 5G is just like a newest generation of mobile network technologies, right? But it still supports like, a lot of the things that have been there before. So it's not like entirely about like new RAN technologies, which are absolutely there, but it's also like, being able to interoperate with like, multiple kind of network technologies, including the legacy technologies. So the key thing is like, which was started off with, is really to have like much higher throughputs than 4G LTE, right? So like multi-gigabit second per second speeds are like entirely possible with 5G. It's once like, it's widely deployed and getting used, it's probably going to be hard to reach for everybody, but like technology itself is capable of supporting like gigabits per second. And the other key point is like it can support like much lower latency as compared to like 4G and LTE, right? So like so like if something needs to be done within like 10 milliseconds or so, like it's not going to be very easy to do with LTE or 4G. So like this enables a lot of new applications like factory automation, like augmented reality, virtual reality, and so on. And we'll talk about it a little bit, like because like this 5G lower latency is kind of enabling a lot of functions that were not previously possible using wireless technologies, but it also puts a lot of pressure to get closer to the user to be able to reach these latencies. Because if you just have low latency on the radio side, it's not going to cut it, because like once you go over an optical cable, then speed of light comes into play. So you cannot go faster than speed of light. So you have a latency like the further you go away from the user. And so the other key thing, right, like what 5G allows is like uses like multiple frequency bands, right? Like so we have the regular bands, like around like less than like a gigahertz, and then like 2.4 gigahertz like ranges, and then you have like mid ranges, like 6 gigahertz kind of ranges, but some of them have like very high frequencies, like millimeter wave kind of stuff. So the idea is like the larger the frequency, right, like you can find like more contiguous pieces of frequencies to have like higher bandwidth, right? But the downside is like the higher the frequency, the smaller the coverage area, right? Like so in a lot of cases, like a 5G base station is probably going to have coverage area of like few hundred meters, like, and this makes it like really decentralized. So imagine, right, like if a base station can cover like only like a very small area, then it means that in a large metro area like New York or like San Francisco, you're going to have like thousands of base stations just to provide the coverage. And then what you need to do is like start processing the data very close to the edge in order to not get overwhelmed by the additional bandwidth. So just like talking about like the market drivers here, this is like some of these are like studies, right? You just see like on the right side you see this picture where like the number of connections, like 5G connections worldwide, right? Like you see like a small start here, and then like this is like a typical hockey stick kind of curve that starts off. So you do see like quite a bit of like people moving on to 5G like very soon. So like we expecting probably about like 500 million connections like as early as next year. And so like a lot of the stuff is like coming from China right now, right? Because they have like a really early deployment advantage, but I think the rest of the world is probably going to like catch up like very soon as well in the deployments. We see quite a bit of deployments going on. And on the other side, if you look at like how the data centers are going to grow, like you see like a huge move towards like edge data centers, right? And I'll get to it why, but if you just like look at it, like the edge data centers are going to push a lot of the demand in the data center space, and most of the data that's generated in like these kind of 5G networks is probably going to get close to about 75% of it is going to get processed very close to the edge. And just like looking at the market, like this is like pretty significant market, like for pretty much everybody, right? Like so if you look at the hardware, the software platform, the connectivity and application services, there's this huge economy that's coming up like along with the edge. So we do see like pretty much everybody trying to fulfill some kind of like market share in this space. And so that's why like there's been a lot of efforts going on to optimize really everything towards the edge, including 5G. So looking at like kind of from the application side, like what is really driving the edge, right? Like so we talked a little bit about it, like the VR AR kind of story. This has like been coming for a long time. It was never like very satisfactory before. So you just try to kind of keep the latency low to make sure that like people have some kind of realistic responses to the stimuli, right? Like when somebody moves, they don't want to see something like a second later, so it really throws people off. So the idea is to really keep the latency low. And similarly, like industrial control, you have some camera watching something and something goes wrong, you really want the control loop to be like very quick, right? And also connected cars is similar. So like, there could be like lots of video feeds, like LiDAR feeds all coming in. And this may or may not be related to the actual control aspect. The control might be distributed into the cars itself, but there's still a lot of data coming in. So there's like a high performance involved on the throughput side. And interactive gaming is like kind of both. Like, there's like a lot of like bandwidth that's required, but there's also like, pretty low latency that's required. The lower the latency, like the better the gaming experience. And similarly, remote medicine, if you're doing remote surgery with a robot, like, you really want to be as low latency as possible towards the actual end subscriber. So one thing that kind of comes across, like, the number that comes across is like 10 millisecond or 5 millisecond, like depending on who you speak to. And so but the bottom line is like very, very simple, right? So something cannot be just done using a public cloud solution. So so a lot of the stuff has really moved to the cloud, and this is like really like something that happened across industries, like, like Amazon is AWS, like Microsoft is Azure, and like Google GCP. They've all like taken quite a bit of market share in here, but like a lot of these low latency applications require some kind of like edge presence, right? So you cannot just go to like some like availability zone like quite far away to do this processing. I'm sure there's a lot of the loads that can go there, but there's some kind of latency sensitive load that's going to require some edge presence. And we know for a fact, like a lot of these people are actually building out like stuff, like for example, like wavelength is like something that would like have some kind of local presence at the edge data centers. But like just a pure public cloud solution is not going to be enough, because it's simply just too far away. So if you take somewhere like New York, which is not really like a very distant place, the nearest like, public cloud availability zones are really far away, right? Like it's pretty much like more than 20 millisecond away in ping times. So it's like something has to change here in the way in which networks are getting built. And this is not really about like, the business models of the public cloud players, like just like large data centers in centralized locations is not always going to be enough. So there's going to be some kind of distributed presence as well. And so a lot of the operators like see there's like a good business opportunity for them to get into this space, because they have one important advantage here, right? They own the real estate. So if you look at it, a lot of the operators have like, real estate that's very, very close to the subscriber. So this could be like a central office, like, if you look at like ONF Cord, that's kind of where it started off, right? Like, there's like central offices, can we put a data center in there? So that could be like an edge side, like, or just below the base stations and like near cell towers and so on. So you can really go very far out close to the users to put the workload. So this is like a survey, like, IHS Market did like, I would say last year or so. So like you see like about like 97% of operators want to have some kind of workload execution very, very far out in the network. So these are like, kind of like not very surprising numbers, but this number really like, going far out, that this percentage of operator want to run stuff there is like very, very, very interesting. So so 5G, like, in addition to all the other things we talked about before, one important thing that 5G provides is like something that's called slicing. So we think it's like a really key aspect of 5G itself. So 5G, what it lets you do is it kind of lets you take like a cut of the network across like from end to end, like starting with the RAN through the core network, as well as like the applications and so on. And you can make a complete slice of it. So you can have one slice of your 5G network dedicated for IoT, one slice like dedicated for like video streaming, one slice dedicated for interactive gaming and so on. And each of them with like different characteristics if you need. So you can have like different kind of core network processing for each of these things. And that's like, one thing that's like really, really key and a huge promise of 5G. And so we can do that by like kind of like, taking like the SDN concepts like that we've learned, like, when we are building like regular networks, to also do this to 5G. So the 5G RAN virtualization has come really, really far. And we are trying to do that, like, at the edge data centers and the centralized data centers as well. Like, how can we split this in a very, very efficient manner? And the idea is really to say like, okay, like, we can split compute like pretty much at the hardware level, and then like, start allocating pieces of the network to them along with the bandwidth that's required, and building something with a programmable network where the individual slices can themselves be programmed and be able to do different things. That's kind of like really where we are headed. And 5G kind of like gives you the underlying framework for enabling the slicing. So, so what is really special about the edge, right? Like, because like, why can't we just take the things that we have today in the data centers, like large data centers, like, and just put it at the edge? So there's like 3 different components in here that make like the edge different. So one of them is power. So like, there's a lot of times when we are talking to like multiple operators, like, and this is across the globe, right? There's like a significant constraint on the power. So like a lot of the, like even though somebody might have a rack or half a rack in there, a lot of the data centers at the central office and so on, they are not made to have like very high power applications. So they've been built probably like 20 years ago or 30 years ago, and like the amount of power that's available to run this edge site is pretty low. So like you're talking about like 5 kilowatt, 6 kilowatt, 10 kilowatt, and so on. So like, we really need to be very efficient on the power. And second thing is like space, right? Again, so like, we cannot like start stacking more and more like regular x86 servers to like take up the, like, a lot of the loads, because x86 becoming like the, if you look at the VNF movement, right? Like when everybody moved from specialized hardware to generic hardware, the x86 like can do everything, right? But like at some point, there's like limitations in power and space. That means that you're not going to just scale up by putting like more pieces of hardware. So we need to start thinking about doing stuff more efficiently using the right combination of hardware. And the third thing we talked about is kind of like driven really by the application side. The edge-focused applications have very low latency requirements. That's kind of like the reason why they go there. So this is not really, we have an edge side, we randomly put applications there. I think like since there's like a premium of space and power at the edge, like only the applications that are going to require like, high throughput and low latency will get scheduled there. So everything else is still going to get scheduled at a centralized location like before. So like, this is kind of like a playbook, right? Like, how do we actually go about, optimizing the edge, right? Like we want to do something that like kind of takes like, what we've learned from like everything we've done with programmable networks, along with 5G. Like, a lot of us like came from a strong wireless background. So we've gone through multiple generations of it to understand like, how can we optimize like an edge solution for 5G. So first of all, kind of try to unify the compute and networking and potentially the storage too. The idea is to get rid of duplicate functions and enable scale down, right? So the second thing is to integrate the access termination. So like, when we have a 5G network coming in, taking a whole bunch of servers just to do the access termination, like, doing the GTP termination, like NCAP or DCAP, doesn't make a lot of sense, because we want to keep these servers to be monetized, right? Because like if you're doing an edge deployment to enable the ROI, you really need to monetize as much as possible instead of spending it on the networking overhead. And also like as like kind of a side effect, right, of like, unifying these things, like you're reducing the overall complexity and bringing on the OpEx at the edge side too. But really the goal is really to reduce the complexity, because if you have like multiple subsystems running all around, it becomes very difficult to manage the complexity of the system. And as a side effect of it, you also save cost, because if you're starting to integrate and optimize everything into like a single kind of system, you can save quite a bit of cost, because a lot of the redundant functions are like, already getting rid of, like in the networking and the compute. And also try to provide some kind of workload orchestration natively from the system, so you don't have to run a separate workload orchestration from the system itself. And here I want to go back to programmability for a second. So this is like when we started off, like programmability was really something for us, right? Like, we wanted to do stuff very, very quickly. We want to do this in an efficient manner, and we want to do this in a high level language, so we can kind of be independent from the hardware. But programmability also matters in the edge, because that's the only thing that's letting us converge all these functions in. So imagine if we had like non-programmable hardware. So imagine if you had like a fixed function ASIC, there's no way we'll be able to do any kind of functions like for access termination, for example, inside this, right? So like, so the idea is like programmability not only gives us like all the things we talked about earlier, right? Which is the hardware independence, the lack of vendor lock-in, and like feature velocity, but it also gives us like a tool for enabling convergence, right? So when we have like new functions that come in, like that are required, instead of like having separate hardware for this, or like, sending it to a centralized data center, we can quickly deploy the functions very, very close to the edge and react very, very quickly. And so like having a lot more savings, like in complexity, as well as like in performance and costs. So I'll just give you like an example of like, how like, we like optimize the edge, right? So these are like, like a 20 RU rack is kind of like a half a rack, like, and we take like, a traditional way of building stuff on one side and the optimized way, which is like kind of what we are working on right now, to do it on the other side. So, so you have like some fixed function networking hardware, right? Like, it cannot like add like new functions in there. So you need to run like some kind of networking control plane on top of it to make sure that like, all the overlays and fabric management is all done. And then you need to start running workload orchestration, right? Like, which is like, could be, you could do something like OpenStack or like, something like Kubernetes, depending on whether you have virtualized loads or like containerized loads. So that's going to take like a bunch of servers in there. And then you're going to run the access termination. So this is like, where the 5G network gets connected to. So you need to do quite a bit of like actual data plane processing in here. So you could use like something with DPDK and so on. And you're going to take a bunch of servers to do access termination. So here I put in 3 servers, assuming like half a terabit of traffic. So 500 gig per second at the site. So we can like size up or down based on that. So that leaves you about, from the 20 RU rack, like it leaves you about 8 servers that's available for monetization. But by converging everything into a programmable forwarding plane and networking system, we can save quite a bit of the overhead and get almost double the number of servers that's available for monetization. So like, this is like another complete talk by itself, but like if people have questions, we can like certainly talk about it. But the idea is like really we are taking the access termination and integrating it straight into the regular networking, so that like the switches that can be the top of the rack switches for the edge side, they're also able to do the 5G UPF functionality to terminate the 5G connections directly into something at the edge side. So if you do something like multi-access edge compute, like MEC kind of sites, like the networking system itself terminates everything and can handle the traffic directly to the application workloads. And it also takes care of like the WAN functionality, so we can like do like the SD-WAN kind of functionalities from the same kind of networking subsystem. So it tries to squeeze in a lot more functionality because of the possibility of programming things. So we can put in the things that are required for the edge and take out the things that are not required for the edge from this, because we have a programmable system. And that kind of gives you like quite a bit of more servers that are available for monetization. And we can do this for like any kind of like a space and power footprint to show like how much savings we can have by having a programmable networking system that's conversion optimized. So that's pretty much what I wanted to talk about, and I'm really open for questions.
Thanks, Suresh. That was a really interesting talk. Thanks for covering kind of both the technical side as well as the business aspects and opportunity. So I think that was definitely useful. I wanted to start with a question about the last slide you presented, the optimized edge slide. Mm-hmm. So I think this compression that you're achieving is pretty fantastic, actually. It looked like almost like 100%
or 50%, whichever way you look at.
Yeah, 200% reduction, or sorry, you 100% increase in number of servers going from 12 to 4. So you're using 1/3 the number of RUs. Is that also reflective of the power and cooling requirements? Or are the boxes the same?
No, absolutely. Like it really like same thing for the power and cooling too, right? Like and like so if you think about it, right? Like so if like a regular switch, right? Like an open computer reference switch consumes about the same power as like a server would do. Like in a lot of cases less, but like a high-end x86 server consumes about like the same amount of power. So like the power footprint is roughly equal. Like it's probably like off by like a little bit, maybe sometimes like depending on if you have like a dual socket 14 core Xeon or like a smaller one, then things might be off, but they're in the same order of magnitude, like on the power and cooling too.
Yeah, that makes sense, and it's pretty fantastic. So when you look at this compression, would you say your biggest wins were from removing the overhead of virtualization? Was it embedding the functions in hardware? Where did the big wins come from?
I would say all of the above, right? Like the first we started off is, so there's like, I would say 3 different aspects to it, right? Like first of all, is the programmability, right? Like, so we are able to do functions that had to be done outside the networking subsystem. So once you have like a fixed networking subsystem, anything else you want to do new, you either need to wait for like new hardware to come in, or you need to put in some kind of like, software-based solution, right? Which is going to take up like more rack space, more power, and more money, right? Like, so that's where, like, that's the only place where the extensibility was. So like some of the functions we could directly take in and integrate straight into our pipeline. So that's the programmability piece. That's like one thing. The second thing is like the function integration, right? Like, so there's some kind of network functions that are never inside like the networking subsystem, right? So this is like the access termination. So this could be a 5G UPF. It could be a BNG, for example, right? Like we don't have a BNG yet, right? But like, something like an AGF, which is a new function Broadband Forum is working on for converging the accesses, right? The AGF like tries to bring in everything into the same kind of 5G kind of session management model. So we could implement an AGF function and also be able to terminate like stuff like GPON directly inside the same kind of converged data plane. So we could have the convergence in the data plane, again, like programmability being the key. So we could start doing the access termination without requiring additional use. And the third thing is like, we decided to have a regular control plane based on Kubernetes instead of trying to build our own. So we could use like the cluster, and we could run the cluster inside the switches. So we have like a regular x86 CPU, like a Xeon D class CPU in there, and we're actually running the Kubernetes controllers directly on the switches and still have room left over for running the containerized workload. So that's the virtualization overhead you're talking about, right? So that's something we cut by choosing to build a distributed like containerized control plane for the system, right? So that's like early architectural decision. But what we can do here is, since we already have the container orchestration system, why can't we use it for the workloads there as well? So that gets rid of one more layer of overhead, because it's like the same Kubernetes OpenShift based system. Like, if somebody can run workloads on it, why not, right? So if somebody wants to run some CDN workload or like a video game workload, which is containerized, like it's just as good in this controller that's running on a switch, because it's small number of like servers we need to manage. We don't need like huge servers to run this. Right? So those are the aspects, yeah.
Yeah. And kind of going right into that third-party application, I mean, we alluded to a lot of the monetization opportunities from an operator perspective. All of the value-added apps, the IoT, the augmented reality, the connected car, all that stuff. How do you see those third-party applications being integrated into this stack? Like, what's the blueprint for that?
Right. Like, so like, frankly speaking, right, like this is going to vary over the place. Like there's like, operators we're talking to who are trying to build their own kind of systems, and some of them they're going to like, big SIs, right? Like, there's like stuff like IBM and Altran, they have like, kind of solution. Lenovo, they're coming up with like solutions to do this kind of edge workloads, right? So at some point, there's going to be like some kind of application development platform that's going to sit on top of it, but it's going to expect some kind of infrastructure management like underneath, right? And that's like, we are seeing like pretty much like OpenShift and Kubernetes like taking over like the space, right? Because it's like very, very efficient, like it kind of compresses the overhead. So the stuff is going to be built on top of this, and a lot of the stuff is going to be outside the edge side, right? Because like it's not critical that these kind of like, the larger MEC kind of platforms, right, like have to be present here. So they can be sitting somewhere else, but orchestrating everything that's happening here, right? Including setting up like, what traffic gets local breakout and what traffic gets sent to the centralized location. And we are seeing some fascinating applications, Brian, right? So like, we saw like, one customer talking about like mass compliance at a factory. So they're building out a 5G network at a factory, like, and there's like video feeds coming in, and this is going and training a model, like, and the model is going to infer if somebody's wearing a mask or not, right, at the site, right? And then it like, triggers something, and the learning can be somewhere else, but the actual like checking if somebody doesn't have a mask happens at the edge, because it can happen much faster, right? Like, so some data is going to get sent further down, like, to like use economy of scale to do stuff, and the other stuff is really going to be at the edge to do the quick decisions.
Yeah, so I think the model of kind of onboarding containers and then orchestrating them locally makes a lot of sense, and that that works really well for CPU workloads, maybe even GPU workloads. How does this extend to cases where somebody wants to augment the pipeline, say on the SmartNIC or on the on the switch in the fabric?
Right, like so, like we have like kind of two different kind of solutions, and they're both dependent on P4, right? Like we expect like the smart NICs or the like any kind of like FPGA offloads to be P4 programmable. So one angle is like you saw the switches in the picture, right? Like we want to have a kind of switch that's going to have FPGAs on board. So that's like a daughter card that you can buy and throw in or not throw in, right? Depending on if you need it, right? But we can actually do some kind of service chaining. So like one example that came out of the ITF is SRv6, right? So the SRv6 can be used to like service chain across stuff. So that you could put in some kind of rules into the basic networking and saying like, hey, this is something that needs to get passed on to the GPU, right? Like imagine you have like a bunch of NVIDIA GPUs like sitting there, and you want some specific traffic rules to match and send stuff there. That's something you can instantiate on the P4 pipeline, say, hey, these things need to get service chain to something else to get processed. And that's something that's like very, very straightforward. We do have an implementation of that where like, we can do the service chaining for these things.
So you're just maybe to summarize or restate what you said. So the idea is for network-based workloads, you would want to identify insertion points into the pipeline, and then you would give the orchestrator a hook and use something like SRv6 service chaining to redirect traffic in the direction of those functions.
Absolutely, yeah. A lot of the times it happens the other way, right? Like the orchestrator kind of figures out and tells us like, what to send off like into the service chain, right? So there's going to be some kind of application level orchestration which kind of identifies, I would say the packet attractors or stuff, whatever you want to call it, right? Like, it's called like PDRs in 5G that tells us like what traffic requires additional treatment, right? And that's kind of what we follow to send stuff over.
Got it. Yeah, that makes sense. So I guess in that sort of same spirit, the traffic that's the orchestrator has to decide, the centralized orchestrator has to decide, do I deploy something to the edge? Do I deploy it to a regional office? Do I deploy it to a central office? How does things like being aware of an application's latency budget or bandwidth requirements factor into your scheduling decisions?
Absolutely, they do, right? Like 100%, right? Like this is something that's a key, and not only the the budget for like performance and latency, also like hardware accelerators play into this. So if you look at like Kubernetes or OpenStack, they already have like primitives like for doing this, right? Like so you can have like labels for kind of hardware, specific kind of hardware, like to like get the affinities for that and for scheduling the workload. So this is like something that's kind of the orchestrators are kind of already aware of. Of course, there's work to do, right? So there's like stuff like device plugin in Kubernetes that will allow like GPU accelerators and so on. And this is like work that's there, but it's not like like fully there, right? Like we still need like a little bit more work to do. But I absolutely think like all the scheduling decisions will be made when applications state specific preferences. So the scheduling will absolutely take care of it.
Yeah, okay. Because that's I think, for CPU memory, even some additional capabilities, that's definitely part of the Kubernetes stack today. But the networking requirements is a bit more of a gap. Oh, go ahead.
Yeah, like absolutely, Brian, right? Like, we were like one of the first people to start using like Kubernetes for networking functions, right? Like, for, like even like having multiple interfaces in a container was like a chore to start off with, right? Intel came up with Multers and we started using Multers and we said like, oh, like, networking is pretty much an annotation. It's really not a first-class citizen in Kubernetes, right? Like, it's, but it's come a long way. Like, there's like work going on in CNCF. There's this network plumbing working group that takes a look at a lot of the advanced networking stuff. And we have some specs over there where we made quite a bit of progress on the Kubernetes side and the networking, right? Like with advanced networking needs. So I think you'll get there because like, it's kind of really the community that drives it. And the Kubernetes community has always been like, application service providers, right? Like, Google, Facebook, Lyft, Uber, and so on, like who've been there. But like, now there's like a lot more participation from the networking folks. And this is going to change. Like you said, like, like 2 years ago, it was like pretty far off. And like, slowly but surely we are getting there.
Yeah. So what would you say the biggest challenges currently face like the Kubernetes CNI?
So the CNI itself, like, it's not like too difficult, but there's like a grab bag of issues like that we go on, like, dynamicity is like one of them, like, how do you like, plumb networks like quickly, like once you have, like, let's say you have a router container, right? Like, running stuff, like, how do you bring up an interface or bring down an interface without restarting a pod? That's like one key thing, right? And how do you like actually scale up these networking? How do you make sure that you don't have like multiple levels of NAT? Because like, a lot of the like abstraction is pretty much like a NAT, like for service indirection, right? So how do you make sure that you don't have like 3 levels of NAT going in? But I think like, and the policies is another thing. Network policy has like quite a bit of work to do, like in there, like, how do you actually like steer traffic between places and so on? And how do you say like what's allowed, what's not allowed? So I think like network policy is like one key place where we need to improve. And also the dynamicity is like something we need to greatly improve on there.
Okay. Yeah, that makes sense. Maybe switching gears a little bit, you talked about a big win or a big add to 5G is the ability to do network slicing. Can you talk a little bit about how sort of the abstraction for network slicing fits into this model?
Yeah. So think of it like, okay, so if you look like a bunch of programmable pipelines, right? Like we are starting to think like, slicing could be like a part of a programmable pipeline, because one important thing about slicing is not just like plain virtualization, because the slices can be different, right? You could do different things in there. So you could always do like an MVNO. We always had this concept called MVNO. So this is like an operator who doesn't own much physical infrastructure, but they kind of take a slice of everybody's network. But they were the same network functions being done on all of them, right? Like, all the slices change by size, but not by quality. But like on a 5G slice, you could do different things, right? You could do like different kind of processing for low latency workloads than you can do for like, something that's like mobile broadband, which is really feature rich, and you want to do some kind of content adaptation and so on. So that's like, the big difference, like in the 5G slicing, where like all these slices can be independent and have like different functions, and it's baked in directly into the standard, and like everybody has to do it, right? So this is not like some vendor doing some specific things, or like, it's like a very weak abstraction where like, everything has to be the same. So that's kind of really key. And like, that's like goes everywhere. Like, when even when I set up like, like a UPF with like some SMF, like, this is something that's always given, right? Like I figure out like what data network it needs to connect to, right? Like, so those kind of things are like built in. So it kind of like is pervasive everywhere in the system. So it's really easy for everybody to do.
So maybe let me just add on a follow-up question. So you mentioned that like each of these operators, the MVNOs, for example, may want to provide a different set of functions, or maybe a single operator may want to have a different set of functions or a different pipeline for, say, IoT versus AR traffic.
Mm-hmm. Yep.
How do we manage or map those different logical or different slice pipelines to one or a few physical pipelines?
So like obviously the cardinality matters, right? So as long as it's like, the number of physical pipelines fits, like we should be okay. But if not, like things get a little bit more complicated. So and that's kind of why we are going in the direction of the FPGA to enable this, right? Because FPGA allows like more flexible partition of the logic. So we could decide to take like some amount of like transistors and logic in there and some amount of memory in there in a very, very flexible manner and allocate it to whatever pipeline. But obviously, like in an ASIC like Tofino, which is like a multi-pipeline already, right? It becomes straightforward to start mapping things in as long as the number is smaller than the actual physical number of pipelines, right? But like, so in order to move to the next stage where like things are like really truly dynamic and we can go like really small as possible, we need like something like an FPGA, like for example, like a static extend allows us to like dynamically do these things, right? Yeah. So that's one thing. And the second thing is like another key thing with the slice is like sometimes like we don't need to do anything, right? So some operator might say like, hey, I'm just going to give you a slice, do whatever you want, and somebody could just run plain IP, right? Like, just like not do any function. So like, let's say Tesla takes a slice of everybody and just like runs the data to using some everything afterwards. That's going to be possible too.
Yeah, that's pretty exciting. So, the heterogeneity piece is really interesting. And managing different chassis, different types of ASICs, FPGAs, stuff like that. Have you found that P4 has enabled you to do this in a fairly uniform way, or have there been pitfalls that you've encountered?
Yes and no, right? Like, P4 is like, without P4, this is probably not going to be possible, right? Like, so unless we have a unified abstraction of how things are going to look like, things are not going to work, right? So like P4 has absolutely enabled us, but it's not been without pitfalls, right? We needed to work on like getting a P4 compiler for a given backend is like not like a trivial task, right? And we had like amazing partners to help us, like, Intel being like a key one, like, Barefoot, like, when they were separate, and now together as Intel, they've been like another a key partner. And we had this company called Netcope, like, out of the Czech Republic. They were doing a compiler for this. And we have some now also part of Intel. And then we work with a Japanese company called Nagase, like, who build logic for the FPGAs, the IP for that. Like, when we have a lookup, specific, like a exact lookup, or like, TCAM, or like a longest prefix match, like the P4 needs to get blocked on, like moved on to the VHDL blocks. And Nagase, like, who's like amazing, like they're doing the blocks for us. So like, it's not like an easy task. Like, it's not like, oh, I took take P4 code, like run a compiler and it's going to work. But we spent like 2 years, right? Like, trying to make sure that we can run on a FPGA. But like once it's done, the payoff is like amazing. Now, like, it's like very straightforward to like, when the FPGA improves in quality, like, I don't know, when Statix 20 NX comes out, right? Like whenever, like, I don't even know, I'm just making up a name, right? Like we can just use the features of the of that chip, like with like more memory, faster, and so on, without worrying about it. Like, now it's just like the hardware backend we need to modify. So P4 is essential, but like there's going to be pitfalls when bringing on new hardware on board always. But I think we managed to get across that. And we did have a demo, like, I can probably point you to something like, that we did along with Intel to show like a pipeline of a UPF passing through both a Tofino and FPGA.
Oh, cool. Yeah, that would be that'd be great. Maybe we can include that in the description.
Sounds good. Excellent.
So, it seems like, Kaloom has got most of this 5G stuff figured out. So, we can all expect this to be deployed right around the corner, I'm sure. But, there's a big amount of change here, right? There's the introduction of new network technology. There's a large reorganization of network functions. There's embedding of things that weren't embedded before. And I think, you talked a lot about, and thanks for going through, some of the approaches for how you're planning to do that. But what do you see, are the biggest challenges that remain? Like, what are the unsolved problems that, you're working on or you could use help with?
So like, so the big thing is like, there's like a lot of incumbent vendors, like, who have like, we're not going into a lot of greenfield deployments, right? Like, a lot of brownfield deployments. So we need to figure out like, how we fit into existing architecture. So greenfield is like pretty straightforward, right? Like we go in and we kind of like let everybody pick their best in class. So there's kind of networks that are like deploying like that. They treat 5G like a complete greenfield kind of deployment. But there's also like, the complex parts come in when we have to work with like legacy architectures like that are there, and like work with like vendors, like, who obviously have some kind of like, I would say, interest to kind of keep things the way they are, like without disaggregating. I think like anybody who's doing a disaggregation play without having the complete portfolio is going to run into the same things, right? Like, because we are dependent on like everybody being like making people to have best in breed networks, right? But there's like a huge recognition in like pretty much a lot of the network operators around the world that like, having a multi-vendor network that's like has best in breed components is very good. And that's really what's like, kind of the win in our sales, right? Like really keeping us going, because they talk to the vendors and say, hey, I really think like, openness over these like interfaces is like very important. And that's kind of key for us. Like, and without that, like, we're not going to go anywhere, right? Like, if you're a disruptive vendor somewhere, like, you really depend on like openness everywhere, like everybody else has to come to the table. And there's like a lot of open source implementations that we use and everything, but there's also a lot of commercial vendors who are coming on board and like being like, pretty open about like, interoperating and building best in class networks. On the RAN side, it's been pretty easy. Like, we run pretty much with everybody's RAN. On the core side, it's like, it's taking a little bit longer.
Yeah. Cool. Anything else you wanted to add that you've thought of as we've been talking here?
No, thank you very much. Like, it is like great talking to you, and always like when you have like good questions, it kind of like, helps me like, digest the things a little bit better, and like, kind of anticipate questions in the future too, right? Like, because like if you have a question, like, we're going to get the similar kind of questions from customers, partners, and so on. So like, I think it's really good that we have this talk.
Cool. Yeah. Thanks, Suresh, for all your time and putting the slides together. Really appreciate it.
Perfect. Thank you very much, Ryan. So thanks a lot, and thanks, Michelle, as well.